A quark is an elementary particle and a fundamental constituent of matter. Quarks combine to form composite particles called hadrons, the most stable of which are protons and neutrons, the components of atomic nuclei. Due to a phenomenon known as color confinement, quarks are never directly observed or found in isolation. They can be found only within hadrons, such as baryons and mesons. For this reason, much of what is known about quarks has been drawn from observations of the hadrons themselves. Quarks have various intrinsic properties, including electric charge, mass, color charge and spin. Quarks are the only elementary particles in the Standard Model of particle physics to experience all four fundamental interactions, also known as fundamental forces, as well as the only known particles whose electric charges are not integer multiples of the elementary charge. There are 6 types of quarks, known as flavors: up, down, strange, charm, top, and bottom. Up and down quarks have the lowest masses of all quarks. The heavier quarks rapidly change into up and down quarks through a process of particle decay, the transformation from a higher mass state to a lower mass state. Because of this, up and down quarks are generally stable and the most common in the universe, whereas strange, charm, bottom, and top quarks can only be produced in high-energy collisions. For every quark flavor there is a corresponding type of antiparticle, known as an antiquark, that differs from the quark only in that some of its properties have equal magnitude but opposite sign. The quark model was independently proposed by physicists Murray Gell-Mann and George Zweig in 1964. Quarks were introduced as parts of an ordering scheme for hadrons, and there was little evidence for their physical existence until deep inelastic scattering experiments at the Stanford Linear Accelerator Center in 1968. Accelerator experiments have provided evidence for all 6 flavors. The top quark was the last to be discovered at Fermilab in 1995. Classification. The Standard Model is the theoretical framework describing all the currently known elementary particles. This model contains 6 flavors of quarks, named up, down, strange, charm, bottom, and top. Antiparticles of quarks are called antiquarks, and are denoted by a bar over the symbol for the corresponding quark, such as U for an up antiquark. As with antimatter in general, antiquarks have the same mass, mean lifetime, and spin as their respective quarks. But the electric charge and other charges have the opposite sign. Quarks are spin 1/2 particles, implying that they are fermions according to the spin statistics theorem. They are subject to the Pauli exclusion principle, which states that no 2 identical fermions can simultaneously occupy the same quantum state. This is in contrast to bosons, any number of which can be in the same state. Unlike leptons, quarks possess color charge, which causes them to engage in the strong interaction. The resulting attraction between different quarks causes the formation of composite particles known as hadrons. The quarks which determine the quantum numbers of hadrons are called valence quarks. Apart from these, any hadron may contain an indefinite number of virtual quarks, antiquarks, and gluons which do not influence its quantum numbers. There are 2 families of hadrons: baryons, with 3 valence quarks, and mesons, with a valence quark and an antiquark. The most common baryons are the proton and the neutron, the building blocks of the atomic nucleus. A great number of hadrons are known, most of them differentiated by their quark content and the properties these constituent quarks confer. The existence of exotic hadrons with more valence quarks, such as tetraquarks and pentaquarks, has been conjectured but not proven. However, on 13 July 2015, the LHCb collaboration at CERN reported results consistent with pentaquark states. Elementary fermions are grouped into 3 generations, each comprising 2 leptons and 2 quarks. The first generation includes up and down quarks, the second strange and charm quarks, and the third bottom and top quarks. All searches for a fourth generation of quarks and other elementary fermions have failed, and there is strong indirect evidence that no more than 3 generations exist. Particles in higher generations generally have greater mass and less stability, causing them to decay into lower generation particles by means of weak interactions. Only first-generation quarks occur commonly in nature. Heavier quarks can only be created in high-energy collisions, and decay quickly. However, they are thought to have been present during the first fractions of a second after the Big Bang, when the universe was in an extremely hot and dense phase. Studies of heavier quarks are conducted in artificially created conditions, such as in particle accelerators, having electric charge, mass, color charge, and flavor. Quarks are the only known elementary particles that engage in all 4 fundamental interactions of contemporary physics: electromagnetism, gravitation, strong interaction, and weak interaction. Gravitation is too weak to be relevant to individual particle interactions except at extremes of energy and distance scales. However, since no successful quantum theory of gravity exists, gravitation is not described by the Standard Model. See the table of properties below for a more complete overview of the 6 quark flavors' properties. History. The quark model was independently proposed by physicists Murray Gell-Mann and George Zweig in 1964. The proposal came shortly after Gell-Mann's 1961 formulation of a particle classification system known as the Eightfold Way, or, in more technical terms, Souflav's symmetry. Physicist Yuval Ne'eman had independently developed a scheme similar to the Eightfold Way in the same year. At the time of the quark theory's inception, the particles U included, amongst other particles, a multitude of hadrons. Gell-Mann and Zweig posited that they were not elementary particles, but were instead composed of combinations of quarks and antiquarks. Their model involved 3 flavors of quarks, up, down, and strange, to which they ascribed properties such as spin and electric charge. The initial reaction of the physics community to the proposal was mixed. There was particular contention about whether the quark was a physical entity or a mere abstraction used to explain concepts that were not fully understood at the time. In less than a year, extensions to the Gell-Mann-Zweig model were proposed. Sheldon Lee Glashow and James Bjorken predicted the existence of a 4th flavor of quark, which they called charm. The addition was proposed because it allowed for a better description of the weak interaction, equalized the number of known quarks with the number of known leptons, and implied a mass formula that correctly reproduced the masses of the known metons. In 1968, deep inelastic scattering experiments at the Stanford Linear Accelerator Center showed that the proton contained much smaller, point-like objects and was therefore not an elementary particle. Physicists were reluctant to firmly identify these objects with quarks at the time, instead calling them partons, a term coined by Richard Feynman. The objects that were observed at SLAC would later be identified as up and down quarks as the other flavors were discovered. Nevertheless, parton remains in use as a collective term for the constituents of hadrons. The strange quark's existence was indirectly validated by SLAC's scattering experiments. Not only was it a necessary component of Gell-Mann and Zweig's 3-quark model, but it provided an explanation for the kaon and pion hadrons discovered in cosmic rays in 1947. In a 1970 paper, Glashow, John Iliopoulos and Luciano Maiani presented the so-called GIM mechanism to explain the experimental non-observation of flavor-changing neutral currents. This theoretical model required the existence of the as-yet undiscovered charm quark. The number of supposed quark flavors grew to the current 6 in 1973, when Makoto Kobayashi and Toshihide Masukawa noted that the experimental observation of CP violation could be explained if there were another pair of quarks. Charm quarks were produced almost simultaneously by two teams in November 1974, one at SLAC under Burton Richter, and one at Brookhaven National Laboratory under Samuel Ting. The charm quarks were observed bound with charm antiquarks in mesons. The two parties had assigned the discovered meson two different symbols, J and psi, thus, it became formally known as the J-psi meson. The discovery finally convinced the physics community of the quark model's validity. In the following years a number of suggestions appeared for extending the quark model to 6 quarks. Of these, the 1975 paper by Haim Harari was the first to coin the terms top and bottom for the additional quarks. In 1977, the bottom quark was observed by a team at Fermilab led by Leon Lederman. This was a strong indicator of the top quark's existence. Without the top quark, the bottom quark would have been without a partner. However, it was not until 1995 that the top quark was finally observed, also by the CDF and DO teams at Fermilab. It had a mass much larger than had been previously expected, almost as large as that of a gold atom. Etymology. For some time, Gell-Mann was undecided on an actual spelling for the term he intended to coin, until he found the word quark in James Joyce's book Finnegan's Wake. 3 quarks for Muster Mark. Sure he has not got much of a bark, and sure any he has, it's all beside the mark. James Joyce, Finnegan's Wake. Gell-Mann went into further detail regarding the name of the quark in his book The Quark and the Jaguar. In 1963, when Dye assigned the name quark to the fundamental constituents of the nucleon, I had the sound first, without the spelling, which could have been ʻkwɔrk. Then, in one of my occasional perusals of Finnegan's Wake, by James Joyce, I came across the word quark in the phrase, 3 quarks for Muster Mark. But the book represents the dream of a publican named Humphrey Chimp Den Earwicker. Words in the text are typically drawn from several sources at once, like the portmanteau words in Through the Looking Glass. From time to time, phrases occur in the book that are partially determined by calls for drinks at the bar. I argued, therefore, that perhaps one of the multiple sources of the cry, 3 quarks for Muster Mark, might be 3 quarts for Mr. Mark, in which case the pronunciation, ʻkwɔrk, would not be totally unjustified. In any case, the number 3 fitted perfectly the way quarks occur in nature. Zweig preferred the name ace for the particle he had theorized, but Gell-Mann's terminology came to prominence once the quark model had been commonly accepted. The quark flavors were given their names for several reasons. The up and down quarks are named after the up and down components of isospin, which they carry. Strange quarks were given their name because they were discovered to be components of the strange particles discovered in cosmic rays years before the quark model was proposed. These particles were deemed strange because they had unusually long lifetimes. Glashow, who co-proposed charm quark with Bjorken, is quoted as saying, "We called our construct the charmed quark, for we were fascinated and pleased by the symmetry it brought to the subnuclear world." The names bottom and top, coined by Harari, were chosen because they are logical partners for up and down quarks. In the past, bottom and top quarks were sometimes referred to as beauty and truth, respectively, but these names have somewhat fallen out of use. While truth never did catch on, accelerator complexes devoted to massive production of bottom quarks are sometimes called beauty factories.